Each year, more than 20 million tons of copper are mined worldwide, a familiar metal that has quietly become the lifeblood of the modern world. So how are ore deposits buried deep underground brought to the surface and transformed into the foundation of a multi-billion-dollar industry? From mining sites, copper ore is extracted and transported to processing facilities. At the plant, the ore is crushed and then separated, typically through flotation, to obtain copper-rich concentrate. After that, it is smelted, refined, and further processed into various technical materials, ready to enter highly precise manufacturing processes in modern industry. Today, let's join Agriculture Insight in exploring the journey of copper, from its raw beginnings to becoming a core material that powers the systems of the modern world. Chile is currently the world's largest copper producer, accounting for around 25 to 30% of global output, followed by Peru and China, forming a strategically important global supply chain. However, as demand continues to surge driven by electric vehicles and renewable energy, while new deposits are becoming increasingly difficult to access, many experts warn of a potential supply shortage in the future. Compared to other metals, copper has a lower electrical conductivity than silver, but it offers far greater cost efficiency. It also performs better and remains more stable than aluminum over long-term use, and is significantly more effective at conducting electricity than metals such as steel. This balance between conductivity, durability, and cost is what makes copper the optimal choice and a foundational material in most modern electrical systems. Behind every copper-based product lies a vast industrial process operating on a massive scale. This journey begins with the extraction of copper ore from either open-pit mines or deep underground deposits. In open-pit mining, the process begins with stripping away the overburden, the layers of soil and rock covering the copper ore body beneath. This material is not simply discarded. It is carefully managed and transported to designated waste dump areas to ensure slope stability and overall mine safety. Once the ore body is exposed, geologists and engineers conduct detailed geological surveys to determine rock structure, hardness, and the distribution of mineral deposits. Based on this data, a precise drilling pattern is designed, where hole depth, angle, and spacing are carefully calculated to maximize fragmentation efficiency while minimizing risks such as ground instability or impacts on surrounding areas. Industrial explosives are then loaded into each drilled hole and detonated using millisecond delay sequencing. This controlled, multi-stage blasting creates a series of timed explosions that break the rock into manageable sizes, reducing the need for extensive primary crushing in later stages and improving overall processing efficiency. Immediately afterward, large hydraulic excavators move in to collect the broken ore and load it onto heavy haul trucks. Each truck can carry hundreds of tons per trip and operates continuously along internal mine roads designed in spiral patterns, allowing stable transport from the pit floor up to the surface. The entire system, from stripping and drilling to blasting and hauling, operates as a tightly integrated chain, where each stage is synchronized to maintain a steady flow of ore for the downstream processing stages. If open-pit mining exposes the surface, underground mining moves in the opposite direction, descending deep into the earth to reach ore bodies located at great depths. From a main shaft, horizontal and vertical tunnels are excavated through layers of rock, forming a complex, maze-like network. Within this environment, specialized drilling machines continue boring into the ore body, followed by the use of explosives to break the rock in confined spaces, requiring far higher precision and control compared to open-pit operations. Once fragmented, the ore is not transported by large haul trucks as on the surface. Instead, It is brought to the surface using conveyor belts, rail carts, or vertical hoisting shaft systems. At the same time, the entire underground network must be continuously ventilated to supply fresh oxygen and remove toxic gases, along with rock reinforcement measures to ensure worker safety. It is these harsh conditions and confined spaces that make underground mining far more complex and costly, yet it becomes the only viable option when copper deposits lie deep beneath the earth. After leaving the mining site, copper ore is transported by conveyor belts or haul trucks to large-scale processing plants. Here, the entire operation runs almost continuously with automated systems tightly controlling each stage of the process. Inside the plant, the copper ore passes through a multi-stage crushing system to reduce its size in a controlled manner. Initially, primary crushers break large rock fragments into smaller pieces, which are then fed into secondary and tertiary crushers to produce finer particles. The ore is often mixed with water to form a slurry, which improves transport and processing efficiency while helping to fully liberate the copper-bearing minerals for subsequent separation. Particle size is strictly controlled, as even minor deviations can significantly affect metal recovery efficiency. After fine grinding, the ore is sent to the flotation stage, a critical step for separating copper from the surrounding waste rock. At this stage, the slurry is mixed with water and chemical reagents, while air is injected to generate fine bubbles. Copper-bearing particles attach to these bubbles and rise to the surface, while impurities sink to the bottom. The resulting froth layer, enriched with copper, is then collected to produce a higher-grade concentrate, ready for the next stages of smelting and refining. Next, the copper concentrate is fed into large industrial furnaces, typically reverberatory furnaces or modern smelting systems, where temperatures can exceed 1000 degrees Celsius to separate the metal from unwanted components. In this environment, continuous chemical reactions take place, producing molten copper and slag, with the latter carrying impurities that are removed from the process. The result is crude copper, not yet highly pure but ready for the next stage of refining. The molten copper from the smelting furnace is continuously poured into large molds, typically through automated casting systems, to form thick plates known as anodes. Each plate can weigh several hundred kilograms and is cooled with water to maintain its shape before being lifted out by overhead cranes. Although already in metallic form, these anodes still contain impurities, such as sulfur, iron, and other metals, so they cannot be used directly and instead serve as raw electrodes for the next stage of refining. The anode plates are suspended in electrolytic tanks filled with an acidic solution, alternating with cathodes made of pure metal. When an electric current is applied, copper from the anode gradually dissolves into the solution and deposits onto the cathode as pure metal, while the anode itself is consumed, its surface becoming rough, porous, and noticeably thinner over time. Insoluble impurities fall to the bottom, forming anode slime, which may even contain precious metals such as gold or silver. After several days, the cathodes are removed, now coated with copper of about 99.99% purity, ready for the next stages of processing. After electrolytic refining, pure cathode copper is melted and continuously cast into long copper rods. The molten metal is poured through cooling molds, solidifying into bright, uniform rods with a standard diameter and consistent quality. Depending on the production line, these rods may be cut into sections for storage or kept in continuous form for direct transfer to the wire drawing stage. The most critical step is wire drawing, in which copper rods are pulled through a series of dies with progressively smaller openings to reduce diameter and elongate the metal. This process occurs in multiple stages, from coarse wire to very fine strands, increasing mechanical strength, but also causing the copper to harden due to friction. To counter this, annealing is performed intermittently to soften the material and restore ductility, preventing breakage during subsequent drawing stages. Once the desired size is achieved, the wire is cooled, cleaned, and tested for electrical conductivity and tensile strength, then wound into large coils, ready for use in the production of electrical wiring, industrial cables, and electronic components. Copper is not only used as a conductive material in industry, but also plays a role in high-precision manufacturing processes, notably in forming the metal jacket for bullets in engineering and defense applications. The process begins with material selection. Copper is preferred for its superior strength and excellent corrosion resistance, allowing the projectile to withstand high pressure and temperature during firing. The raw copper is then fed into rolling systems where it is transformed into thin metal sheets with thickness precisely controlled down to fine tolerances. Next, the copper sheets are punched into circular blanks using high-precision stamping machines, ensuring uniform dimensions with minimal tolerances. The blanks are then cleaned and may undergo light annealing to improve ductility, preparing them for subsequent forming processes. This stage is critical, as initial precision directly affects the quality of the final product. After being cut into circular blanks, the copper pieces are fed into a deep drawing press to form cups. A cup-shaped structure with a closed base and thin walls. Under high pressure, the material is stretched and reshaped, creating the initial form of the metal jacket. During this process, thickness and dimensions are tightly controlled to ensure uniformity, while lubrication or annealing may be applied to reduce friction and prevent cracking. This is an important intermediate step before further elongation and final finishing. Following the cupping stage, the next step is multi-stage drawing. The cups are passed through a series of dies with progressively smaller diameters to elongate the body, thin the walls, and gradually increase height. This process occurs continuously across multiple stages, with pressing force and speed tightly controlled to ensure uniform wall thickness and to minimize unwanted deformation. Throughout the process, the surface is lubricated to reduce friction, and intermediate annealing may be applied to restore ductility and prevent cracking caused by work hardening. As a result, the component gradually achieves the required dimensions, shape, and structural stability before moving on to the subsequent forming stages. Once the cups have been sufficiently elongated, they move to the necking stage. Here, the upper section is pressed through dies to gradually reduce its diameter, forming the characteristic tapered neck with precise dimensional control. This step defines the final geometry and ensures proper fit and stability for the subsequent finishing processes. After the metal casing has been fully formed, the core is inserted inside through a process known as core seating. At this stage, the core is pressed tightly into the casing under high compressive force, ensuring precise positioning and stable contact between the two materials, while minimizing any gaps or misalignment during assembly. This process requires strict control over pressing force, speed, and dimensional tolerances, as even a slight deviation can lead to off-center alignment or structural deformation. In addition, the weight and placement of the core are closely monitored to ensure balance, uniformity, and overall stability of the product before it moves on to the final forming stage. Finally, once the core has been perfectly secured and all parameters meet absolute standards, the entire component enters the final inspection stage, where even micrometer-level deviations are examined with extreme precision. This is not merely a quality check, but a moment of quality affirmation, ensuring the structure achieves near-perfect durability, concentricity, and stability. Any minor deviation, no matter how small, is immediately corrected to preserve complete consistency across all units within the production batch. When every standard has been fully satisfied, the component is officially ready for the final finishing process, closing the manufacturing journey with a crucial transformation from a precise technical assembly into a fully completed product of the highest refinement. While China dominates the world with more than 50% of global pencil production, operating like the planet's gigantic manufacturing machine, on the other side of the hemisphere, Brazil has emerged as South America's pencil superfactory, home to the largest Faber-Castell facility in the world, where forests are transformed each day into millions of writing instruments distributed across continents. Yet behind these impressive figures lies a fascinating paradox. Pencils have never actually contained lead. The familiar name originated from a 16th century misunderstanding when graphite was first discovered and mistaken for the metal lead, an error that persisted for hundreds of years. And it is precisely that simple carbon core that creates something remarkable. A single small HB pencil can draw a line up to 56 kilometers long, roughly the distance from downtown Los Angeles to Disneyland Anaheim. To understand why a small pencil stands behind a multi-billion-dollar industry, we must return to where the story truly begins, not in the factory, but in the forest. Each year, billions of pencils are produced, creating an enormous demand for carefully selected timber from across the planet. The forests of California red cedar become the ideal starting point, where straight, soft, and dimensionally stable trunks are cultivated for 20 to 30 years for one single purpose: to become humanity's writing tools. Massive old-growth trees with trunk diameters reaching 100 centimeters are typically felled using high-powered chainsaws. Meanwhile, smaller trees are gripped by modern harvesters that cut them at the base, strip away their branches, and section them into logs within seconds, faster than the blink of an eye. In the heart of the wilderness, steel, hydraulics, and roaring engines merge together, turning the forest into a colossal raw material production line operating without pause. Once felled, the journey of the timber has only just begun. In remote and rugged terrains where no roads exist, logs are airlifted by specialized helicopters, lifting massive trunks off mountainsides like enormous cargo suspended in midair. In most industrial forests, however, giant mechanical arms clamp onto each trunk, bundle them together, load them onto heavy-duty transport trucks, and move them along forest roads built specifically for the logging industry. Convoys of timber roll through dense woodlands, cross the icy landscapes of the northern regions, pass over great rivers, and eventually reach seaports, where they continue their voyage aboard colossal cargo ships sailing across oceans. After standing still in nature for decades, these tree trunks now become passengers in a global logistics network, bound for processing plants where the story of a pencil is truly written. While timber leaves the forest to become the pencil's body, elsewhere on Earth, its soul is awakened from beneath the ground. If wood forms the outer casing, graphite is the spirit that writes every stroke, two separate materials converging to create a complete pencil. This mineral is primarily extracted from open-pit mines in China, Brazil, and Mozambique, nations with abundant reserves and relatively low extraction costs. To reach graphite veins buried deep underground, miners descend into dark tunnels where sunlight barely exists. They ride industrial elevators hundreds of meters below the surface, set fuses and explosives, then retreat nearly 300 meters before the earth trembles violently. When the blast subsides, they return through clouds of dust and shattered rock to collect the glossy black graphite blocks. Heavy ore carts are hauled back to the surface using industrial lifts, where even a brief power outage can transform routine work into a life-threatening challenge deep underground. At the surface, the graphite is crushed and processed to separate pure carbon crystals from impurities such as soil, rock, and metal. The result is high-purity graphite powder, often exceeding 90% carbon content, ready for the next stage, forming the pencil core. As timber arrives at factories and graphite travels across continents, the two materials finally converge to form the perfect structure that protects and carries the writing core. From this point on, the crafting process truly begins. Inside the workshop, massive wooden beams are fed into automated sawing systems, where laser beams and infrared sensors continuously measure straightness, density, and grain patterns in real time. Only sections that meet strict standards are sliced into slats 5 to 6 millimeters thick, the ideal dimension to create 1/2 of a pencil body. A deviation of just 0.1 millimeters can cause the pencil to break or sharpen poorly. Each cut is therefore not merely machining, but a precise transformation, the moment a tree trunk begins its evolution into a writing instrument for humanity. After cutting, the wooden slats pass through multi-blade automatic grooving systems. High-speed rotating cutters carve uniform longitudinal channels with tolerances measured in thousandths of a millimeter. A misalignment no wider than half a human hair could throw the graphite core off balance and cause the pencil to snap the moment it is sharpened. While the pencil body is being shaped, on another production line, the graphite core is undergoing its own transformation to become the true heart of the pencil. To create the writing core, graphite powder is blended with clay in ratios so precise that major brands like Faber-Castell and Mitsubishi Pencil guard their formulas almost like high-end perfume recipes. The more clay added, the harder the core and the lighter the stroke. The more graphite included, the softer and darker the line. This is why familiar markings such as H and B appear on pencil barrels, details many people rarely notice. H, hard, is used for technical drawings requiring fine lines. B, black, is preferred for bold artistic shading, and HB represents the balanced middle ground. Next, the cores are dried to remove moisture, then fired in kilns at temperatures reaching 1000 to 200 degrees. This process stabilizes their structure and increases hardness. Finally, the cores are soaked in oil or wax to reduce friction, allowing for smoother writing and less dust during use. Unlike standard pencils, colored pencil cores contain no graphite at all. Instead, they are made from pigments blended with wax or oil, materials that, in the history of fine art, were once more valuable than gold. Each shade of red, blue, or yellow carries its own precise pigment wax-oil ratio, because every color particle reacts differently to light and friction. This means that a box of 120 colors represents 120 independent material formulas. The mixture is thoroughly blended, extruded into strands approximately 17.5 centimeters long, dried, and then tested for color accuracy and brittleness before being inserted into the wooden casing. Because colored cores are not fired at high temperatures like graphite, they remain softer and more fragile, requiring transportation and assembly processes executed with near handcrafted precision. Once completed, the graphite or colored core is precisely placed into the pre-carved grooves using a high-accuracy automated system. A second wooden slat, coated with specialized adhesive, is then laid on top, firmly enclosing the core in the middle to form the well-known wood sandwich structure, a design that originated in the 18th century and has endured to this day thanks to its exceptional stability. The entire wooden block is then subjected to hydraulic pressing with forces reaching up to 5 tons, ensuring the core remains perfectly centered and durable throughout the pencil's lifespan. From that moment on, wood and core are no longer separate components, but fused together as one, officially becoming a complete pencil. After the wood sandwich block is fully stabilized under pressure, it moves into the shaping stage. The long wooden strips are cut into standard 17.5 centimeters lengths, then fed through high-speed milling systems to form their final shape. Most commonly the hexagonal design, which prevents rolling, saves material, and provides a more balanced grip for extended writing. Next, each pencil undergoes strict quality control. Cameras and precision sensors detect off-center cores, microscopic cracks, or abnormal vibrations before the product is approved for market release. After shaping, the pencil enters the coating stage. Each one is finished with 3 to 6 layers: primer, color, and a final protective coat. The iconic yellow, long associated with pencils, was originally used to promote Chinese graphite, considered the finest in the world during the 19th century. Today, manufacturers also use red, black, blue, or even natural wood finishes. The paint is not merely decorative. It protects against moisture, prevents decay, and allows the barrel to withstand thousands of sharpenings without cracking. Once fully dried, the pencil moves to the branding stage. High-speed printing machines stamp the brand name, product code, and hardness grade, such as HB, 2B, or H, onto the barrel, part of a classification system that can include more than 20 distinct levels. A single small marking determines whether the pencil is suited for everyday writing, technical drafting, or artistic sketching. In the final stage, many pencils are fitted with the savior of every writing mistake: the eraser. The metal ferrule is stamped from thin coils of aluminum or brass, forming small ridges that grip the barrel tightly. Inside sits an eraser made from synthetic rubber, blended with softening agents and ultra-fine abrasives, designed to lift graphite cleanly from the paper. The entire ferrule and eraser unit is then automatically crimped onto the end of the pencil by precision machinery. For pre-sharpened pencils, the last step is revealing the writing core. Industrial sharpening machines with fixed blades create an almost perfect angle, ensuring smooth, consistent lines from the very first stroke. Sensor systems automatically adjust the cutting depth based on the hardness of the core to prevent breakage. Before leaving the factory, every pencil must pass a final inspection: barrel straightness, core alignment, paint consistency, and the firmness of the eraser. Only those that meet strict standards are sorted and packaged into boxes of 6, 12, or 24, in recycled paper sleeves, clear plastic cases, or even premium tin boxes. From distribution centers, they are shipped across the globe. Remarkably, an average pencil can write more than 45,000 words or draw a line up to 50 kilometers long. From classrooms and laboratories to art studios, billions of human ideas begin with nothing more than a single stroke of graphite. And now join us as we explore this remarkable rebirth. A journey that may seem vast in scale, yet begins in the simplest of places, the household waste bins of millions of families. For this circular process to begin, the first requirement is a stable supply of used bottles and jars. In modern recycling systems, collection largely relies on fleets of specialized trucks, machines designed exclusively for glass. On average, a major operator such as Biffa in the United Kingdom must cover around 3,000 households per day to ensure not a single fragment of recyclable glass is left behind. This pressure becomes even more intense during the summer months, when warmer weather drives up demand for cold beverages. The resulting surge in discarded bottles and jars forces collection trucks to operate at full capacity, making multiple collection rounds per day instead of the usual single run. But door-to-door collection is not the whole picture. In most EU countries, networks of reverse vending machines are now installed throughout supermarkets, activating source-level sorting right at the point of disposal. Consumers simply place an empty bottle into the machine, The system scans it, sorts it, and returns a small cash refund, typically around 10 to 25 cents, depending on the country. A soda bottle you've just finished drinking, instead of becoming waste, can instantly turn into loose change for your next purchase. This approach not only encourages people to participate voluntarily in collection, but more importantly, it supplies recycling plants with a stream of pre-sorted, cleaner, and far more uniform glass than ordinary mixed waste. From here, the journey of transporting tens of tons of bottles and jars to specialized processing plants begins. Large trucks, each capable of carrying between 20,000 and 30,000 bottles per trip, operate continuously, moving between supermarkets and collection points to consolidate the material for recycling. The processing cycle is formally initiated when heavy-duty industrial loaders move in on stockpiles of waste glass rising several meters high. Each bucket can hold multiple tons of material, which is transported in a controlled manner across the yard to maintain a steady feed rate into the plant. At the intake point, the glass is discharged directly into receiving hoppers. Driven by gravity, the mixture of fragments slides down reinforced steel chutes where conveyor systems come into operation. From this moment on, the glass stream, still mixed with sand, dust, and contaminants, is carried deep into the processing line, where successive stages of cleaning and sorting will ultimately determine the quality of the entire downstream recycling process. After being broken down, the waste stream makes its first stop at a multi-stage vibrating screening system. Here, high-frequency vibrations separate natural contaminants, such as dust, gravel, and sand, from the main glass flow. This stage serves as a surface cleaning step, allowing the material to be more clearly exposed and prepared for more advanced sorting processes. However, mechanical equipment at this stage cannot fully remove larger or lighter contaminants, such as paper labels, plastic films, or pieces of wood. As a result, a manual inspection zone follows immediately after the vibrating screens. Specialized workers are positioned along the conveyor belt to visually monitor the stream and manually remove any remaining foreign objects. The combination of mechanical separation and human judgment ensures that the material meets cleanliness standards before entering the more sophisticated downstream separation systems. But even after screening and sorting, troublesome obstacles always remain hidden within the pile of broken glass. Bottle caps. These are the enemies of the furnace, as they do not melt like glass and instead introduce contaminants capable of ruining an entire batch. At this stage, massive electromagnets suspended above the conveyor belt come into operation. Generating extremely strong magnetic fields, they lift and extract every steel bottle cap or screw upward, completely separating them from the glass stream moving below. Thanks to this decisive step, the cleanliness of the material is raised to around 80%. Clearing the way for the critical crushing stage that follows. Once most contaminants have been removed, the glass enters a critical stage of structural transformation. Crushing. Large fragments are fed into hammer mills where high-speed rotating hammers deliver repeated impacts, breaking the glass down into uniformly sized particles. To maintain quality control, any pieces exceeding the specified size are captured by screening systems and redirected back into the crushing chamber. The result is glass cullet with a fineness comparable to manufactured sand. Reducing glass to this granular form not only allows it to melt more quickly in the furnace, but also helps save up to 40% of the energy required compared with using entirely virgin raw materials. Immediately after crushing, the material stream is passed through a high-capacity extraction system. Here, powerful air currents strip away and blow off any remaining microscopic label fragments still clinging to the surface. This final cleanup step ensures the glass reaches maximum purity before entering the laser-based sorting stage. The final, and also the most sophisticated stage in the cleaning process, is optical sorting. At this point, glass fragments are spread thin and allowed to fall like a waterfall in front of a system of high-power laser sensors. In a split second, these sensors scan each fragment to accurately analyze its color and material composition. As soon as a differently colored piece of glass is detected, or more dangerously, a stray piece of ceramic, the system immediately activates compressed air nozzles. These air jets fire with millimeter-level precision, blowing the contaminants out of the main stream in just milliseconds. Absolute precision at this stage is vital, because even a tiny amount of color deviation or ceramic contamination can completely ruin the transparency and quality of the entire batch. After passing the laser system's inspection, the clean glass fragments move along the conveyor belt to the final collection area. Here they are separated and stored individually according to 3 color codes: clear, green, and brown. A step that may seem simple, but in fact directly determines the value and efficiency of recycling. Few people know that clear glass accounts for the largest proportion and has the highest economic value. However, with just 1% colored glass mixed in, a melting batch will immediately become cloudy and unable to regain its original transparency. Therefore, color separation is mandatory to control purity, enabling factories to recycle directly into new products of the same type without incurring the cost of removing color impurities. After being refined, recycled glass cullet cannot be fed directly into production, but must first go through a raw material blending stage. The basic composition starts with pure silica sand to ensure transparency. Next comes soda ash to lower the melting temperature, and limestone to increase the mechanical strength of the finished product. Depending on specific requirements, manufacturers add minerals such as alumina, dolomite, or metal oxides to adjust color and physico-chemical properties. In this batch mixture, recycled glass accounts for 20 to 70% of the total weight. This proportion allows the mixture to melt faster, directly saving about 40% of operating energy and reducing carbon emissions compared with using only virgin raw materials. Once the components reach the standard proportions according to the preset formula, the mixture is thoroughly blended and moved to the melting stage. The batch is fed into a high-capacity gas-fired furnace system. Here, the temperature is maintained at around 1,250 degrees Celsius to carry out the material transformation process. Because the heat radiated into the surrounding environment is extremely intense, the operating crew must wear specialized heat-insulating protective clothing and thick gloves to control the melting pot safely. After about 24 hours of continuous firing, the raw material mixture melts completely and turns into a highly viscous liquid. During the next 5 hours, the molten glass is kept at a stable temperature for the refining stage. This is a mandatory step that allows air bubbles to escape, ensuring the purity and uniform structure of the glass stream. To transform the molten glass stream into products with specific shapes, the mold system is an indispensable component. Based on designs created in specialized CAD software, molds are manufactured from cast iron or special alloy steel. These materials possess extremely high heat resistance, up to 1,400 degrees, ensuring they do not deform when in continuous contact with molten glass. After fabrication is completed, the mold sets are installed on the production line, ready for the forming stage carried out directly inside them. When the mold system is ready, the process enters the double blow stage, the standard method for producing hollow containers such as soft drink bottles or pharmaceutical jars. The process begins by cutting the molten glass stream into gobs of uniform weight. These gobs enter the preliminary mold at around 1,000 degrees Celsius, the ideal temperature at which glass reaches stable viscosity, allowing smooth forming. Inside the preliminary mold, a first blast of compressed air is blown forcefully from above, pressing the molten glass tightly against the mold walls. The result of this step is the formation of a parison, a hollow structure in which the bottle neck is clearly shaped, while the body remains soft and retains a large amount of heat. Immediately afterward, the glass parison is transferred to the final mold set, located right next on the production line. Here, a second blast of compressed air is injected directly into the center of the parison, stretching the softened glass outward until it fully conforms to the fine details inside the mold cavity. Although this process appears very fast from the outside, in reality, the entire system of valves and sensors must be synchronized with precision down to 1/1000 of a second. It is precisely this extreme level of technical control that enables corporations such as Coca-Cola or Heineken to ship hundreds of thousands of bottles every day with absolute uniformity, ensuring that every single bottle meets the same standards before global distribution. Although today glass packaging accounts for only about 15% of Coca-Cola's total output, it is by no means outdated. On the contrary, for many discerning consumers, glass remains an irreplaceable choice. It keeps drinks cold longer, does not retain odors, and does not alter flavor. As a result, the fizz and sweetness are preserved intact, a purity that plastic or aluminum has yet to fully replicate. First, we move straight into the beating heart of the circular economy, where household waste is no longer buried in landfills but reborn as biological fertilizer. From anonymous trash bags, an industry worth over $60 billion a year is emerging, turning environmental burden into sustainable revenue and new life for the planet. To turn waste into money, the first step is not technology, but separation. Fruit peels, leftover food, paper, and leaves are sorted out to be composted or recycled. In contrast, metals, plastics, and non-biodegradable materials are collected separately to prevent contamination, clearing the way for the real value hidden in waste. After preliminary sorting, tens of tons of household waste are transported each day to processing plants, where they officially enter the most critical stage of their regeneration journey. Here, waste is no longer a chaotic mix of debris, but a raw input for a tightly controlled industrial process. First, the sorted waste is conveyed onto industrial belts and fed directly into high-capacity shredding systems. Inside the crushing chamber, alloy steel blades rotate at high speed, powerful enough to break down bones, hard shells, and even the toughest organic materials. This process reduces the waste into uniformly sized particles, increasing surface area and creating ideal conditions for microbial activity in later stages. More importantly, shredding reduces waste volume by up to 40%, saving storage space and significantly lowering transportation costs. A modern industrial shredder can process between 10 and 20 tons of waste per hour, equivalent to the combined output of 1,000 manual laborers. Once shredded and homogenized, the organic waste mixture is sent directly to the composting area, where it is formed into long windrows or transferred into enclosed composting tunnels. Here, the life-critical process of organic fertilizer truly begins. Native microorganisms are rapidly activated, penetrating every particle and breaking down organic matter in a controlled biological process. Driven by intense microbial activity, the temperature of the compost mass gradually rises and stabilizes between 55 and 65 degrees Celsius. This temperature range is high enough to eliminate most pathogens, harmful bacteria, and completely destroy any remaining weed seeds. At the same time, turning and moisture spraying systems are operated regularly to maintain optimal oxygen levels and humidity. Through this process, what was once a chaotic pile of waste transforms into a closed biological system, cleaner, safer, and ready to move into the maturation stage of high-quality organic compost. After the active decomposition phase, the compost is transferred to a curing and biological stabilization stage, where its final quality is shaped. Beneficial microorganisms continue working quietly, completing the transformation of organic matter into stable humus. After the curing stage, the compost is screened to define its final value. The humus stream passes through rotary screening systems, separating material that meets the size standard of under 15 millimeters, accounting for up to 80% of the total mass, while coarser fractions are recirculated for further processing. As a result, the organic fertilizer achieves high uniformity, stable moisture levels below 25%, and is free of contaminants, or ready for packaging. From raw waste at the start, the final product becomes a standardized agricultural input that can be applied directly to the fields. After leaving the screening line, compost is not yet released to the market. It must first pass through the final checkpoint, the QC lab. Here, samples are carefully analyzed for biological stability, including moisture, pH, and potential risks from heavy metals or residual pathogens. Only when all indicators meet regulatory standards, with moisture maintained around 50 to 60%, is the compost approved for use. This final control step eliminates risks at the last stage, ensuring a safe and consistent product. Once certified, the compost moves directly to the packaging line, where each bag completes its regeneration journey, ready to return to the fields as new agricultural value. Organic waste treatment reduces the amount of waste sent to landfills by 40 to 60%, easing pressure on the environment and urban systems. The resulting compost not only supplies nutrients, but also improves soil structure, enhances water retention, reduces nutrient runoff, and lowers dependence on chemical fertilizers. When properly regenerated, household waste is no longer a burden, but a circular resource that nourishes sustainable agriculture. More than 1/3 of the world's freshwater supply is used for irrigation, while clean water sources are becoming increasingly scarce and pollution continues to spread. Faced with this paradox, humanity has found a new path, transforming dirty water into irrigation water, regenerating the flow of life from what was once considered hopeless. To turn thousands of tons of foul-smelling wastewater generated every day into water safe enough for irrigation and the environment, the initial treatment process serves as a critical line of defense. As wastewater silently flows through underground pipes into treatment plants, it carries not only contaminated water, but also diapers, wet wipes, plastics, and fabrics. This is why public restrooms are forced to post warnings not to dispose of paper or waste into toilets. Each year, careless flushing habits generate hundreds of tons of non-biodegradable debris, enough to cripple wastewater treatment systems worth millions of dollars. Water that passes this first control stage then flows into grit chambers, where the flow is deliberately slowed, allowing heavy materials such as soil, sand, and stones to settle at the bottom. After coarse waste is removed, the wastewater enters a critical screening stage in the grit chamber. Flow velocity is tightly controlled and combined with precisely regulated aeration to trigger natural separation. Heavy particles such as soil, sand, and gravel quickly settle to the bottom, while the lighter water continues downstream. Each week, the system can collect and treat nearly 1 ton of inorganic grit, preventing damage to equipment in subsequent stages. From here, the wastewater flows into the primary settling tank, where gravity becomes the primary filter. After approximately 5 to 6 hours, most of the heavy sludge settles at the bottom, while clarified water separates above. Automated scrapers continuously remove settled sludge and floating scum, transferring them to digestion tanks. Through this step alone, more than 50% of suspended solids are removed, creating a stable foundation for the biological treatment and reuse stages that follow. From the settling tank, the wastewater enters the aeration basin, the living heart of the entire treatment system. Here, every cubic meter of water contains hundreds of millions of microorganisms working continuously in an oxygen-rich environment, created by constantly rotating aerators that keep the water in motion. These microbes convert waste into energy for the cleaning process. Within just a few hours, toxic ammonia and most organic compounds are broken down directly in the flowing water. No longer a matter of passive filtering or settling, the aeration basin functions as a precisely controlled artificial ecosystem, where more than half of the plant's overall treatment efficiency is determined before the water moves on to its final stage.